Yeah. There, we got that. Okay, let's take the house lights down and we shall begin.
Put in LEDs.
Laser pointer works, okay. Good evening, ladies and gentlemen, and welcome to the Space Telescope Science Institute's public lecture series. It is my joy and pleasure to be your host. I am Dr. Frank Summers of the Office of Public Outreach. For the gentleman who just came in late, you didn't get a pretty picture yet. The pretty pictures are down there on the corner, and tonight's pretty picture is the Butterfly Nebula, also known as NGC 6302. This is a dying star, which is of significance for our speaker's talk tonight because he's talking about, I'll just go straight to it, Planetary Tales from the Stellar Crypt, Exoplanets Surviving the Death of their Host Star. This is John Debes, who has spoken to us before with all sorts of interesting titles, but I gotta say, John, your title is so long that you get a small font. Okay, all right, you get a shorter title, you get a bigger font on the slide here. Next month, we have Rachel Austin talking about why we need to understand stars to find the next Earth. And in May, we have Tom Brown talking about On the Trail of the Missing Galaxies, the oldest stars in the neighborhood. And you'll see that both of them will also get similarly small fonts on their title slide. But Nicole Lewis in June will be talking about probing worlds beyond our solar system. She'll get a little bit of a bigger font because she used a shorter title there. All right. And if you are going to come to those talks, as those of you here found out tonight, and those of you on the web might find out if you come, that the San Martin Drive, south of the Space Telescope Science Institute, will be closed until approximately September 2016. If you come to visit us, come to the auditorium, you must approach from the north, from the University Parkway, okay? All the details are available at this web address from Johns Hopkins, but all you really need to know is what's here. Just come at us from the north, all right? You can find out information about our upcoming lectures on our webpage. If you just put Hubble Public Talks into your favorite search engine, you should come up with this webpage. This webpage was redesigned last month. Excuse me. It has links to the online live events so that those of you who want to watch at home if you are sick next month, you can watch live online, both on YouTube and on the STSCI webcasting site. We have the archives of stuff that's on YouTube or in the STSCI webcast archive. We go all the way back to 2005, so that's like 10 years of astronomical goodness for you to enjoy. We also added to our webpage an easy way to subscribe to our announcements emailing list. The 1 or 2 emails that I send every month reminding people of the upcoming lectures, as well as telling you when the webcasts have been posted and where you can find those webcasts, which is useful. Also, on the right-hand side, you can see the links to the upcoming lectures. About that email list, if you don't want to use the easy way, you want to do it the hard way, you can by going to maillist.stsci.edu, clicking on Public Lecture Announce, and providing your email address there. Or if you really want to be lazy, just write it down on a piece of paper and hand it to me at the end of the talk, okay? And I'll make sure you get added to the email list. If you would like to contact us in other ways, we have the email publiclecture@stsci.edu, comments, questions, and yet another way to sign up for announcements. We've got way too many ways on that. All right. Social media. If you would like to follow us on social media, Hubble has Facebook, 2 Twitter accounts. We're on Google+, we're on Pinterest, and maybe a few more. I myself have a blog, Hubble's Universe Unfiltered, on the Hubble site. I'll have a new posting on Friday. Okay, I don't post very often, but there's a new one coming up on Friday. I'm on Facebook, Google+, and on Twitter, but I'm only occasionally on those devices because social media can just eat up way too much of your time. Unfortunately, the sky is not clear tonight, so we will yet again not have observatory after the talk. This is like 3 or 4 months in a row that we haven't had this. I apologize, I don't control the weather. All right, people may call me the master of the universe, but I cannot control the weather for you. But if you go to marylandmd.spacegrant.org, the Maryland Space Grant Observatory, you will find their webpage and their information about their open nights on Friday nights, I believe. Every Friday night, that's clear, again, subject to the weather, they will let you look through their wonderful telescope there. Okay? So go to their website page and find out about that. Let's take it to our news summary, News from the Universe for March 2016. Our first story tonight. When did this galaxy cluster grow so big? I mean, every time my kids see their grandmother, it's like, oh, you've gotten so big. When did this happen, right? Well, we astronomers do the same things, but this time for galaxy clusters, okay? So here is a galaxy cluster in the nearby universe. It's called the Coma Cluster, okay? And the Coma Cluster is one of the largest galaxy clusters. It's got thousands of galaxies in it, right? And we have estimated the mass of the Coma Cluster, and it's 2 quadrillion solar masses. Now, I know some of you think I just made that up, all right? But I didn't, okay? It goes million, billion, trillion, quadrillion, okay? And the mass estimate here is actually 2 quadrillion. All right, it's 2 times 10 to the 15th solar masses, which is a really big number, but it's a number that I'm going to need later on in this for comparison. Okay, so 2 times 10 to the 15th is your comparison number. Remember that. We'll get back to it. So as the galaxy cluster we're going to talk about is not Coma. It's this one called IDCS 1426. Okay, and this galaxy cluster looks kind of similar to Coma. Lots and lots of galaxies. But there's a clue when we look at the wavelengths in which Hubble observed this galaxy cluster. Because you can see the blue in this image is 606 and 814 nanometers. Blue in visible light is actually around 400 to 450 nanometers. Right? The blue in this image is actually red. The green and the red in this image is actually the near infrared. So all of the filters used to observe this cluster go from the red into the infrared. Why would we do that? Well, because this is a high redshift cluster. All right? The galaxy is so far away that its light has been redshifted from visible light toward the infrared light. So it's better to see this galaxy cluster using infrared light. Okay? This galaxy cluster is measured to be about 10 billion light years away. Okay? It's 10 billion light years away, which means it's seen as it was 10 billion years ago. So the question is, all right, this is about 4 billion years after the Big Bang. The question is, how large of a galaxy cluster can you grow in 4 billion years? Let's find out. So we're going to take that Hubble image and we're going to color it yellow. All right, we're going to do a composite image. All right, and we're going to take all that Hubble image and we're just going to call it visible, even though between you and me, it's really more infrared than visible light in this Hubble image, okay? We're going to use the Spitzer Space Telescope to observe it deeper into the infrared. Okay, Spitzer is an infrared telescope. Doesn't have the resolution of Hubble, but it can see further into infrared, which is better for seeing these higher redshift clusters in order to see the infrared emission from them. And this is going to tell us a bit about these higher redshift galaxies, but to really get great information about it, to try and measure clusters of galaxies, we want to go to the X-rays using the Chandra X-ray Observatory. Now, these clusters of galaxies form by the mergers of smaller clusters, and the gas in between the galaxies as the clusters merge together gets heated up until it's millions of degrees and glows in X-rays. And because the energy put into that gas is indicative of the amount of energy, of the kinetic energy of the galaxies colliding in, the amount of X-ray emission is proportional to the amount of mass in the cluster. Okay? From the amount of X-ray emission of the gas inside the cluster, you could make a good estimate of the total amount of mass in the cluster. All right? So here's that composite image we were building. Here is the X-rays from Chandra in blue, the visible / near-infrared from Hubble in yellow, and the infrared from Spitzer in red, okay? And this shows you the extent of the cluster of galaxies, of the gas between the cluster and galaxies. And using these, we can make the estimate of the mass of this cluster of galaxies, and the mass estimate is 500 trillion solar masses, or 5 times 10 to the 14th, okay? Now, if you remember, 2 times 10 to the 15th was your reference number, all right? This is about 1/4 the mass that's in the Coma cluster. However, the Coma cluster has had 10 billion more years to develop and grow that mass. The question is, can you really grow such a big galaxy cluster, half a quadrillion solar masses in 4 billion years? For reference, the Milky Way galaxy had just formed 10 billion years ago. So in our part of the universe, we'd just gotten one galaxy. Here we've got hundreds to thousands of galaxies together in the first 4 billion years. Obviously it can be done, but it puts constraints on our hypothesis of how quickly things can grow in the universe. And it appears that galaxy clusters, they grow up so fast, all right? We can get a large galaxy cluster very early on in the universe, and this is one of our Hubble press releases from last month, all right? Okay, our second story is not a Hubble story, but it's too important to overlook. A century later, general relativity is still making waves. All right, so 1915, Albert Einstein produces his general theory of relativity. All right, and we have celebrated its centennial last year. Okay, now, how many of you have been here to the public lecture series before? Okay, how many of you have heard me talk about gravitational lensing? How many of you have heard my 3-word summary of general relativity? Can anybody quote it back to me?
Mass bends space.
Mass warps space, or bends space as you said. Yes, okay? So, what I've mostly told you about general relativity is described by this image, okay? That the presence of mass puts a bend, a warp in space, okay? And that light traveling through that warped space takes a curved path, okay? Because it follows the contours of that curved space. This is how we get gravitational lensing. These giant clusters of galaxies warp space so much that the galaxies on the far side, their light comes through and becomes stretched and becomes these streaky, archy things along here, gravitational lensing, okay? And I have sometimes called this visual proof of general relativity because Newton's theory of gravity doesn't produce gravitational lensing. Einstein's theory does. However, there are many other proofs of general relativity, all right, between the time delays and other things. There is, however, one prediction of general relativity that had never been verified, okay? If you can warp space, you can also send a ripple across space, okay? So making a warp in space can actually send a ripple across space called gravitational waves, okay? So they set up detectors, observatories, to try and observe them. And this is the Laser Interferometer Gravitational Wave Observatory, which everyone just calls LIGO because it's a lot less of a mouthful. And in Hanford, Washington, and Livingston, Louisiana, they have 2 detectors set up. All right, I'm not going to get into the details of how it works, but let me just give you the basics. Each arm of these detectors is 4 kilometers long. They take a laser beam, split it, and send it down both arms and back. When it comes back together, they cause it to interfere with itself, and in doing so, they can measure extremely precise distances. Okay, they can measure the distance along those arms extremely precisely. Now, if a gravitational wave was coming through and stretching space, well then one direction would get stretched just a tiny, tiny bit, and the other one would get shortened just a tiny, tiny bit, okay? All right, in the perpendicular direction. So by measuring the distance deviation between these two arms, they could actually measure the idea of a gravitational wave going past. Okay? So, they measured something. September 14th, 2015, they got this signal, which is dubbed GW 150914. All right? And it was measured in the Hanford data, shown in this orange color, and the Livingston data, shown in this blue color. Now, it's important that you measure it in two separate places, because a signal like this could be caused by, some technician dropping a hammer next to the instrument, okay? All right, but a hammer in Washington State is not going to be measured in Louisiana and vice versa. So if you're measuring the same signal in both places, that tells you, hey, it's pretty much coming from the universe. Maybe it's Thor's hammer, or something like that. All right, excuse me. All right, and you can also see from this plot that they measured pretty much the same signal both in Washington State and in Louisiana. What would it be? Okay, well, the hypothesis would be that it is two black holes merging together. Okay, two black holes caught in orbits around each other, giving off energy as they spiral in and then merge together to form one black hole. Right? We're talking about two really, really massive gravitational distortions merging together, creating a gravitational wave big enough to be observed across the universe. All right? How big does it need to be? Well, they did simulations. And here is the Hanford data, and this yellow line going through it is the prediction of the simulation. And there's the Livingston data, and again, the blue line, light blue line going through it is prediction of that data. And you can see how wonderfully this matches. So, in doing the various suites of simulations to try and figure out what this is, they determined that it's a 36 solar mass black hole and a 29 solar mass black hole merging together to form a 62 solar mass black hole. And that would produce that signal, which is the signal that they observed in Washington and in Louisiana. From the amplitude of that signal, they can tell that the merger would have happened 1.3 billion light years away. That's billion with a B. 1.3 billion, so in a distant galaxy, okay, 10% of the way across the observable universe. And if you do the math, you heard that I said 36 and 29 make 62. No, they don't. There's 3 solar masses missing. Where did that 3 solar masses go? Into the fabric of space. That 3 solar masses was put into the fabric of space to create a gravitational wave. Such an amazing event, okay? An amazing event that lasted, less than a second, actually about 2/10 of a second. You can see from the graph, okay? We'll be generous. Yeah, we'll call it full 2/10 of a second. And they say, and I have to quote this, the peak wattage for that tiny little fraction of a second was greater than the combined light of all the stars in the observable universe. But still, all that energy going into it only stretched the fabric of space by 1/1000th the diameter of a proton. That much energy. What they measured was space being stretched by 1/1000th the diameter of a proton. First of all, the fact that we could measure that is absolutely amazing, right? But so much energy to create such a tiny little deviation in space, okay? Gravitational waves are really, really, really small, okay? And we talk about gravity being the weakest of the 4 fundamental forces. Here's your evidence that you have to destroy 3 solar masses, 3 times the mass of the sun, just to stretch space by less than the width of a proton.
That's stretching it right here, but is that the same, stretching the same?
Yes, the amplitude, of course, changes with goes down linearly with distance. Okay, in this case, I'm not exactly sure why it goes down linearly instead of by the square. I couldn't figure that out today, but I'm not a GR physicist on that. Okay, so here is the paper that they released last month. Okay, on the first observation of gravitational waves from a binary black hole merger. First of all, the result is that black holes do merge, okay? We had thought that they would. We had guessed that they would, but there was no evidence for it until this paper was released. Second thing, gravitational waves exist. This is a fundamental prediction of general relativity that had never been tested before. Some call it the final prediction of general relativity that needed to be tested. Gravitational waves do exist. The third thing, due to the time delay between when it was observed in Washington and when it was observed in Louisiana, gravitational waves, as predicted by general relativity, travel at the speed of light. There was no evidence to allow for any deviation from the speed of light for this gravitational wave disturbance. They said it was, I forget what the number of milliseconds. It was like 6 milliseconds differential between the two sites. And finally, general relativity has been proved correct yet again. All right, so now we have a brand new window on the universe. We can observe the stretching of space to see these really high energy events. And you're saying, well, like it was 1.3 billion light years away, it was just one event. However, LIGO wasn't even in production mode at the time. When they saw this, it was in its pre-production mode, okay? LIGO, we have the Hanford and Livingston ones here in the US. Under construction, we have Virgo in Europe. The Geo 600 is online. LIGO India is planned. We have Kagra coming along in Japan. When we get the full suite of them, as well as the planned upgrades to them, which will increase their sensitivity by another factor of 10 or 2, all right, we will be able to see, the prediction is dozens to thousands of these events over the next decade. So we have started. I feel like this is like the exoplanets thing. Where we were in the 1990s with exoplanets, we just saw the first exoplanets around, planets around other stars. We're now being able to see the first of these really, really massive events. Black hole mergers, we should be able to see neutron-star mergers. We'll be able to characterize them and understand what their prevalence is out there in the universe. So we're at a really cool place, and yes, your answer to the question that's always asked, this will probably produce a Nobel Prize maybe about 15 years from now, okay? Nobel Prizes aren't given immediately. They definitely got to wait until make sure that everything holds together. But yeah, I could easily see this producing a Nobel Prize in about 15 years. All right, question?
Other than the distance, we don't know anything about where this happened.
Well, we have a small localization on the sky. That's actually something glad you mentioned that, because by having more detectors around the world, we'll be able to reduce the angular size of it. There was a swath, because having only 2, we could say, all right, here's a swath of the sky, because you're observing basically the sky above you with a gravitational wave detector, right? And if you have them all around the world, whoever sees it or doesn't see it, and when they see it, gives you triangulation, all right, in order to be able to find a finer point in the sky. Folks have looked in the region where it was determined it could have come from, and nobody's found anything of any significance yet for that region. But with more detectors online, we'll be able to do it, and now people will actually believe them. Okay, if they send out a telegram going, "We found no gravitational wave, go look," and people are like, "Yeah, am I going to waste my telescope time on that?" Right now, they will believe them. They will do the follow up. So that'll be a hot topic too. Question in the back?
Does it make sense to talk about frequency and amplitude of these gravitational waves, or did you say they're really minuscule?
The minuscule is the amount of motion is very, very small, but the frequencies are in hertz to kilohertz, okay? And the detectors are only sensitive over a certain range of frequencies. And that was actually another important point, was that another reason why that they believe the graviton has no mass and it travels at the speed of light is that if it had mass, there would be deviation along the frequencies. The frequencies would arrive just slightly different times, and there was no deviation in frequencies seen. Okay. Yes. All right. Let me go down here.
So are gravitational waves the same thing as gravitons?
No. Gravitons are the particle that would carry the gravitational force. But there's a particle wave duality that we talk about. Like the photon is the particle that carries light, whereas light is also considered an electromagnetic wave. In the same way, you have gravitational waves, and you also have a graviton to carry gravitational forces. Okay? Yeah, it's this particle wave duality is it's fuzzy even for us professionals to do it. Okay, question here.
Geo 600 didn't pick anything up.
As far as I know, Geo 600 did not pick anything up. It was not in the paper that I read. One other question in the back.
Don't we have plans underway right now to put detectors in space so that they'll be 3 billion miles apart and therefore much more accurate?
There is the ELISA project, which is the Laser Interferometry Space Observatory or something like that. I don't know much about that, but yes, there are plans to try and put laser interferometers in space to measure gravitational waves from space. I say I'm not an expert on that. All right, I don't want to hold up John's talk any further. You got more questions about gravitational waves? Come see me afterwards. Right now, let me introduce our featured speaker. John Debes got his bachelor's degree from across the street at Johns Hopkins University. Give it up for Johns Hopkins. Yeah! He got his PhD from Penn State about a decade ago and did postdoc down at Carnegie Department of Terrestrial Magnetism down in D.C. He was at Goddard Space Flight Center. What does NPP stand for?
NASA postdoctoral program.
NASA postdoctoral program. I was trying to figure that out when you gave this to me this afternoon. Down at Goddard for 3 years, and then he came up to us in 2011 here at the Space Telescope Science Institute. Besides being a wonderful communicator of science, he is the lead for the Space Telescope Imaging Spectrograph. So, ladies and gentlemen, John Debes.
Thank you very much, Frank. So we're going to have a little death and destruction tonight. The last time I gave the talk, I talked about a zombie planet around Fomalhaut, and this time we're going to be talking about a whole bunch of dead stars and the sort of leftover debris that might be in orbit around them. So when we talk about planets these days, planets are everywhere. It used to be whenever someone had an idea that some observable signature was due to planets, people would kind of laugh at them because, oh, there haven't been that many planets found. We don't know where planets exist, that kind of thing. But now we're in an era where we have thousands of exoplanets that have been discovered. And this is a plot from exoplanets.org just the other day, where I took all the observed planets, both from radial velocity surveys, Kepler, direct imaging, and I plotted them up in sort of a weird way. I plotted them as a function of the effective temperature of the star that they were orbiting around, their mass. The symbol size gives you the mass of the star, and the color bar gives you how big the star is. So most of the planets we have seen are around sun-like temperature stars. They have a large range now in planet mass, thanks to things like Kepler and very precise radial velocity surveys. But we're also starting to probe stars of very different radii as well. And what that's telling us is that we're seeing planets in orbit around stars of many different kinds of evolutionary states, from somewhat young stars all the way up to giant stars, which are sort of sun-like stars that are going through their end phases of life. And so when I was a wee grad student back in the early 2000s, my advisor talked to me and he said, you know, you should take a look and see what happens to a planetary system when its star dies. And that was my fall project in my second year of grad school, and it became eventually my most cited paper on dead planetary systems. So we'll talk a little bit about that. So the end point for most stars is the white dwarf. White dwarfs are also known as degenerate stars, degenerates, right? So not 2016 presidential candidates, but what's happening here is basically the star, as it's burning its hydrogen, fusing it into helium, it's creating this core of fusion ash at the center of the star. And over time, it exhausts all of its hydrogen, and it puffs up to a giant, and eventually starts burning helium into carbon and other things. And eventually that runs out, and it puffs again into a bigger giant, and eventually loses most of its mass, about half if we're talking about a solar-type star. And so you're left with this sort of corpse of a star called a white dwarf, which is basically just the degenerate core of that star. And it's so dense that the electrons are sort of bouncing together, and they're providing the pressure support against the gravity of the mass. So a typical white dwarf is about 6/10 of a solar mass, and its radius is similar to that of the Earth. So these are very dense objects. They're the endpoint to stellar evolution for any kind of star that's not going to explode. And for the longest time, people thought that this process, losing more than half of its mass during this evolution from being a normal star to a giant, eventually to a white dwarf, meant that any planetary system that must be around it must be destroyed instantly from this process. If you do sort of a simple gravitational calculation, you think, okay, if I suddenly remove half the mass from a star, all your planets just go flying out, right? Because they suddenly have way too much energy for the gravity of the star. But it turns out that's not what's happening. And then I'll just point out, and I'll get to more of that story later, but I'll just point out, if you just take a census of the nearest 10 parsecs, or 32 light years, we have, sort of estimates for the numbers of different exoplanets and M dwarfs, brown dwarfs, all the way up to A stars. And unfortunately, they didn't include white dwarfs, my favorite star, but white dwarfs are about as numerous in local space as sun-like stars. So you just want to keep that in the back of your head, and I'll get back to that by the end of our talk. Okay, so we can do a thought experiment about what happens to planetary systems by thinking about our own solar system. Now, we're definitely in an age where we shouldn't only be thinking of our solar system as a prototypical or archetypal planetary system, but the solar system is always a good place to start, right? We shouldn't be limited by what our solar system tells us, but it's always a good place to do thought experiments and stuff like that. So if we have a little picture of the sort of inner solar system, including Jupiter and Saturn, our asteroid belt, and then all the terrestrial planets. We're sitting here 4.5 billion years. Don't argue with me about that. And we're in a nice, stable, kind of happy place. Nothing's going to happen for a while. I do have to say, unfortunately, in a billion years, we're hosed. That's when the sun, due to its fusion, keeps getting a little bit hotter, and we'll have runaway greenhouse gas effect. Global warming on a much more severe scale. Okay, so that's about maybe there. And then eventually, we're going to be in the red giant phase, right? Our sun's going to puff up. I also have bad news. If the heat doesn't get us, the stellar surface will, because it's going to puff up to greater than an AU. And a couple things are happening, right? It's so big, it has tides, really strong tides, so anything close to the star gets eaten. And once it goes in the stellar envelope, we think that's pretty much the end. But Mars seems to survive this process, maybe. And part of the asteroid belt might survive, and I'll go more into that later. And Jupiter's all the way out here. Now, by this point, the sun actually hasn't lost a whole lot of mass, maybe 1/10 or 2/10 of a solar mass. So you'll notice, if we go back, if I can figure out, yeah, hey, that worked. Where's Jupiter? Is it in the same place? No, it's getting a little bigger. It's further out. So what's happening here is the star is losing mass, but it's losing mass pretty slowly, so that the orbit is not perturbed very greatly. We call this an adiabatic process. This is like boiling the frog. You put the frog in the pot, you slowly turn up the heat, frog's fine. Slowly turn up the heat a little more, frog's still fine. Then you keep going until suddenly the frog's dead, right? So we're basically boiling the frog with Jupiter here. It doesn't really care that the sun is losing mass. Its orbit, to conserve angular momentum, just slowly expands a little bit. And it expands by a predictable amount. So if the sun has lost is 80% of its mass, Jupiter has moved to an orbital separation that's 1 over 80%, right? A little over 1 point whatever. I can't do math in front of people. Anyway, eventually, the star loses mass a bit more quickly, and we're left with the remnant white dwarf. but it still has not lost mass too quickly for the orbits not to react to it. And the other thing that I want you to remember is that now we have, instead of a solar mass, we have like a half or a 6/10 of a solar mass object at the center of this planetary system that, for all intents and purposes, I'm going to claim to you survives, and then I will prove it to you in some way later. But basically, everything now is much more powerful, right? So in dynamics, we often care about the mass ratio between a planet and its central object. Okay, so when Jupiter tugs on anything, we think about how much that happens by the ratio of Jupiter's mass to the central mass. So now, the central mass has gotten smaller. Jupiter is already kind of a beefy fella. He's now even more beefy with gravity because he's more of an influential player in this gravitational system. That will become important later, but again, not right now. Okay, so now a little detour. So 5 years after Einstein predicted gravitational waves, Van Manen was at the Mount Wilson Observatory, and he found a curious faint star. And he noted, when he took the spectrum, this is by far the faintest F-type star known at the present time. So what he had actually seen was not an F star. This is a modern spectrum of Van Manen's star. It still carries his name to this day. But it was very unusual because he was able to measure the parallax to this star and found that it was very close to Earth. So given that it was faint in visual magnitudes and close by and moving very fast on the sky, you could tell that it was a very intrinsically faint star, not just visually faint. So this was the first-ish discovery of a white dwarf. And on top of it, it wasn't even a typical white dwarf. It looked like an F-star because it had these metal lines present. You know, if you look at solar-type stars, they have lots of metal lines from different atomic elements. And here we have calcium. These very strong lines are calcium, in fact, the H and K lines. So it looked weird, and it was faint. And within a few years, people realized that these were intrinsically faint stars, about a 10,000th the luminosity of the sun, and that these must be unusual stars, and they called them white dwarfs. And now we know what they are. They are the dead corpses of stars. But they didn't know that then. And they didn't know why there were metal lines. And it turns out you wouldn't expect to see metal lines in most white dwarfs. And that's because they're very dense. So what happens with a white dwarf is you have this core of carbon and oxygen, and then you have a very thin layer of either hydrogen or helium, very low density gas. And if you have any kind of metals in this very thin atmosphere, they get pulled to the center of the star, out of sight. So in a very short time, much shorter than the time we would be able to actually observe these things, these metals, whatever remnant metals might be present in the atmosphere, would disappear. So you would only expect to see pure hydrogen or pure helium white dwarfs, or if you had no thin layer of hydrogen or helium, or there was some sort of convective process, you might also get carbon. But those were the only three elements you might expect to see. So it's actually a puzzle why you might have metals in these atmospheres. So for the longest time, people thought the metals came from the interstellar medium. You know, the interstellar medium, the stuff between the stars, is not empty. There's dust and gas and other things. So as you have a white dwarf plowing through space, it will pick up some of this material. So they said, that must be why you see metals. They're just picking up dust from the interstellar medium. 1919. The 50s, 60s, and 70s was when people came up with the idea that the interstellar medium was accreting stuff. And then 1987 happened. And something unusual was found. So two men, Eric Becklin and Ben Zuckerman at UCLA, were doing an interesting study. They were looking for brown dwarfs. And in 1987, no one had seen a brown dwarf before. And they thought, quite rightly, that it would be easy to find brown dwarfs in orbit around white dwarfs, because white dwarfs are intrinsically faint, And so faint brown dwarfs are easy to find, especially if you look in the near infrared at sort of the same wavelengths that Frank was putting up for that galaxy cluster. So what they did is they were looking at a whole bunch of white dwarfs looking for brown dwarfs. And they made a discovery. They said, we found a brown dwarf, yay! And so they, if you took a measurement of the brightness of the white dwarf at different wavelengths, so this is flux, in wavelength. As you get to longer wavelengths, this is the white dwarf. Its flux goes down. And when you actually observe this particular pulsating white dwarf, G29-38, it does not go down, as you would expect. It gets brighter. This is unusual. So what's happening is that there's an extra cool source of light in this system that's unresolved. And this is called a spectral energy distribution. So when Becklin and Zuckerman first did it, they only had a couple of photometric points. And they said, we think we have a brown dwarf, but it could be dust, could be some other things. Well, it turns out this is dust. There's dust in orbit around white dwarfs. So that's already weird. And it kind of, there was this great paper in 1990, just a few years after this was discovered. Some people thought this was a black hole. Some people thought this was a pulsating neutron star. They had no idea. It was weird. But they decided, in the end, the best explanation was that it was probably dust, right? It was too bright to be a brown dwarf in the end, and brown dwarfs were eventually discovered. Now, you can sort of make a model of the dust disk that must be around it, and you can just assume a very thin, flat disk that's passively re-radiating the light from the white dwarf. And when you do that, you infer that this dust is between 10 white dwarf radii and 30 white dwarf radii. Now, if you remember, a white dwarf radius is about the same radius as the Earth. So that's not very big. And this is a massive 6/10 of a solar mass star. So the orbital velocity here is several hundred kilometers per second. We're starting to get to an appreciable fraction of the speed of light at these velocities. So you have dust nearly at the edge of a white dwarf's surface, whipping around. Okay, how do you get dust? Well, you get dust from planetesimals, maybe? That's what James Graham postulated. Okay, and there it stood for 10, 12 years, and not much else was done. It was an oddity. It was just one. So nature's weird. It always makes weird things. You can explain one thing very easily and then forget about it. And mainly we forgot about it because there wasn't a lot of mid-infrared observing going on. 5 to 10 microns is very hard to do from the ground. And so there it stayed until Spitzer was launched. And then suddenly we had the whole sky in the infrared to look at with very fine detail and with very fine sensitivity. And that's when a whole bunch more of these dusty white dwarfs were discovered. Furthermore, they were discovered not only to have dust, but when you took a spectrum of the white dwarf, you would see metal lines in its atmosphere. And if you thought Van Manen's star was weird, these white dwarfs were even weirder because a lot of them had only pure hydrogen atmospheres. And they were warm, pretty hot white dwarfs. So the settling time, if you dropped a bunch of metals into the atmosphere, the metals would completely disappear within a couple of days. So the fact that you even see metal lines in these white dwarfs meant that they were accreting an appreciable amount of material constantly, not just over 1 billion years or something, but that minute. Okay, so keep that in your mind with the other things. I think I've got more than 6 things in your mind, so you've probably forgotten half of them, but that's okay. I will remind you. In any case, if we go back to the structure idea, we can think about maybe a little bit more about what might be causing these strange dust rings and why this might have a connection to planetary systems. So you have your white dwarf, and you assume that you don't get dust closer than where dust turns into gas. Seems like a reasonable assumption. And you say, okay, how far out do they extend? They tend to extend not too far out, and certainly well within what is known as the tidal disruption radius of the white dwarf. So if we put a planet, or anything very large here, it gets shredded apart and turned into little bits. And so basically, the dust lives within a zone where anything that might stray in that zone would get torn up to little bits. You can have different flavors of your model because this explains more technical details like why you see maybe additional emission lines like this. This is due to silicates. This is how we know it's really dust and not something else, because there's a very strong silicate emission feature. It's a smoking gun for dust, and rocky dust, not anything weird. And now, in the era of Spitzer and then the WISE survey, we have dozens now of dust rings around white dwarfs, and all the dust rings are about within a solar radius, or a little bit larger than Saturn's rings. So there's rocks shredding up somehow and draining onto their white dwarf surfaces, leaving telltale fingerprints of the material that they are made of. So already, that is super cool. This is why I stayed in astronomy, because my second year project told me about crazy stars that should have nothing around them, having really cool things around them, shredding up and doing weird things. So that's it. I was hooked. And so over the next 10, 15 years, we tried to come up with explanations for why this might be happening and learn more about what this dust actually was. So we took spectra of white dwarfs, we looked at the white dwarfs in the infrared, we tried to gain populations to understand what was going on, et cetera, et cetera. And we came up with complicated theories for how the disks evolve with time. This is more for the scientists, but basically we think there's dust. The dust goes beyond the sublimation, it turns into gas. It accretes onto the white dwarf, that's why you get the metals. Some of the gas goes out back, so you have sort of a mixture of gas and dust. Maybe you can see this gas, and in fact, you can. So while people were taking spectra of white dwarfs to look for the metal lines, they also discovered, hey, there's these weird emission lines at 8500. This is, again, calcium, but now in emission. So if you have calcium in emission, that means you've got gas that's glowing, hotter than the star at these wavelengths. And in fact, it wasn't just glowing, it was glowing with this very pronounced double-peaked structure. This is like a smoking gun for an accretion disk, right? Because you have different parts of that disk moving at different velocities, which creates your double sort of peak shape there as you take all these little bits of velocities and spread them out in velocity space or wavelength space, same thing. So we have gas, we have dust and gas going onto the white dwarfs, we have things shredding up, somehow. We even have pictures of the gas. This is so cool. This is just in the last couple of months. There's a technique where if you take lots and lots of spectra and build it all up and decompose everything into velocity space over time with the assumption that you've got some sort of regular periodic event occurring, you can do what's called Doppler tomography. You basically pull out an image from the information, the velocity information. So what we're seeing here is an inside-out picture. So it's not intuitive. So you're not seeing exactly a ring like this going from the center to the outer area. It's more the other way around. This is getting toward the center of the star, and this is getting further away. But in any case, you've got this very interesting elliptical precessing ring of gas around a white dwarf that, with lots and lots of spectra, you can synthesize into sort of an image of what's going on with the gas. And sure enough, just like the double peak structure told us there was some kind of a disk, the reconstruction of the velocities show that there is a disk, but not only that there's a disk, but it's precessing around. This elliptical shape is precessing around and changing the shape of the spectral features that we see. So this is cool. I don't even understand this yet. I need to think about this more. But it's a really interesting way to sort of get a picture of the system that we will never be able to actually resolve with a telescope in any easy time. Now I've taken some spectra as well. And in addition to gas in emission, we've even seen gas in absorption around these white dwarfs. So if you look at sort of the spectrum, again around the calcium H and K lines, you have the main photospheric line, but then you have this little blip, just blue words, right? Now the other thing about white dwarfs, because they're so dense, they have a strong pull of gravity, much like those galaxy clusters, much like the universe redshifts things. White dwarfs locally redshift light. So what happens is the light coming from the white dwarf surface is redder than it would normally be. So its photospheric metal lines are pulled away from the velocity of the white dwarf. So if you have a disk, you've got the gas not reddened quite so much. And it's like a curtain being pulled away. So the white dwarf's gravity pulls the curtain away and allows us to find these weak circumstellar gas features. You can actually do some calculations about, okay, given how wide the gas is in velocity, where might it be around the white dwarf? And sure enough, it's within 100 white dwarf radii or 1 solar radius. And that's roughly about where the sublimation radius of the dust is for this particular white dwarf. And so you can look at a lot of white dwarfs maybe and find similar things. This also says that this particular white dwarf, probably we're seeing the disk edge on right through. We're looking right through it. So that's kind of cool. So we've got these metal lines. If you have enough metal lines, you can actually build up the composition of the dust. The other thing that I should mention is that white dwarfs are extremely sensitive probes to accretion. A me-sized boulder falling onto a white dwarf every second is observable. That's not a lot of material. When astronomers talk about mass, they usually talk about solar masses. Well, these are like kilometer-sized asteroids falling onto the white dwarf every couple days or so, or every year. So it's not a lot of material. It's a suspiciously asteroidal amount of material. And when we look at the composition with these spectra, we find a suspiciously asteroidal composition, a rocky composition that is not unlike the bulk Earth composition or asteroidal compositions in our own solar system. So not only are white dwarfs weird because they have this dust that drains onto their surfaces, and we get to learn about interesting disk and accretion properties in sort of an extreme environment, we also, for free, get dust composition. And if we can link this dust to planets, we suddenly then have a way of sampling the terrestrial chemistry of dead planetary systems. So I'm going to argue now that these are asteroids. These are asteroids that have somehow strayed too close to their white dwarf. They've gotten shredded up. They've drained onto the white dwarf. And we can read their properties from the spectra of these white dwarf. This is incredibly powerful. We cannot go to other planets very easily, especially the rocky ones, and measure what the rocks are. We can do it with Mars. We send a couple robots. It's going to be a little hard to do it around Alpha Centauri or HD 209458. It's going to take a little while to get there. So this is one of our best ways of understanding the chemistry of terrestrial planet formation. This has implications for understanding how different or how typical our own Earth is relative to other stellar systems. And on top of that, there's only a couple of other techniques that get at the sort of chemistry of planet formation or the chemistry of planet atmospheres. So Nicole Lewis in a few months will tell you about how they do the chemistry of atmospheres, but this is sort of like the chemistry of rocks. So it's very exciting. I can't overstate that enough. Very cool. And this is being helped quite a bit by the ultraviolet instruments on Hubble. Because white dwarfs are typically more bright in the ultraviolet, and there are a ton of metal lines in the ultraviolet that are often not accessible in the optical. So instruments like STIS, which I'm in charge of and I'm legally obligated to promote, and also COS, both of them have been instrumental in measuring compositions, especially COS because it's very sensitive. Okay, so these things are also not static in time. We've seen examples of some of these dust disks changing on yearly timescales. We don't understand why. And we even see the emission lines changing with time, which maybe we understand. Some of them are maybe just processing rings, and that's why they're changing with time. But these are kind of disappearing. So there's a quick evolution on a yearly timescale for some of these observable phenomena that we see. Okay, but now we've got this question, right? I just showed you how our solar system would survive post-main sequence evolution, or the death of the star. And it doesn't look too good for stuff that's 1 solar radius away, right? It gets obliterated. So nothing that started out that close is going to survive that close. The star is going to scrub all the material out to 1 or 2 AU because of its evolution. So we have asteroids living somewhere in these dead planetary systems, and they have to start out at a few to maybe 10 AU, and they have to go all the way down to 4.5 times 10 to the minus 3 AU. So remember, an AU is the distance from the Earth to the Sun. So they start out far, and they get really, really close. So how do we do it? This is something that me, as a dynamicist, or a pretend dynamicist, because I'm not a real dynamicist, I just play one as an astronomer, but this is hard to do. You get a little panicky. You get worried. How am I going to do this? This is my thesis. How am I going to finish it? Don't worry. Keep calm and focus on resonances. What are resonances? Okay, so you have Jupiter, right? It goes around in a certain amount of time. And in certain orbits, you have objects that go 2 times for every 1 time Jupiter goes around. They'd be inside if they did that. Or half a time as Jupiter went once. These are special orbits because at a given point in their orbit, they line up with Jupiter, they get a little extra tug. And they get a little extra tug. And they get a little extra tug over and again until they have different orbits. And you can really mess things up this way. Gravity is weak, but it's persistent. Okay, so first, I claimed asteroids survive post-main sequence evolution, or the evolution of their star from middle age to the end of their life. But I didn't really prove it to you. So these are some simple calculations of the survival of fairly large asteroids from Pluto size, give or take, down to very tiny asteroids. And these are survival curves for different situations. So the sun will get to a maximum luminosity during its evolution of about 10,000 times the current luminosity, because it gets really, really big. And so anything that is smaller and closer than this line here will evaporate. Now, let's say you bump it up twice as much, then anything below this curve will survive. Now, we know from your pictures there might be a little bit of gas expelled during the late stages of death. And so that wind, while it doesn't mess anything up too terribly for big planets, can actually drag on small asteroids and pull them into the inner system where they evaporate. So if you're in these sort of regions, below these regions here, for given initial stellar masses, so if we talk about the sun, you have these two curves intersecting, and anything below and interior gets destroyed. But our asteroid belt extends from about here to here. And so there's plenty of big things that can survive these processes. And even if the big things here don't survive, these small things here move in and eventually survive if you get the timing right. So you can get anything that started out here to survive. And also you have to remember things are moving out in response to the mass loss of the star. So you can get a whole bunch of stuff that survives and a whole bunch of stuff from the outer system that moves in toward the resonances, if you're talking about interior resonances to Jupiter, which is what these are. You can also have exterior resonances. So if you have chains of planets, like the typical Kepler planetary system is actually like 5 or 6 super-Earths all mushed together in very tight orbits. So if you have chains of those kinds of planets, you can have lots of resonances interior and exterior. Our own solar system has exterior resonances with the Kuiper belt objects. And there have been people, the list is here, who have measured or modeled the dynamics to see whether asteroids or comets in exterior resonances get kicked into the inner system. And what happens is the gravity of your chain of planets, or a couple of planets, basically kicks from one planet to the next until eventually they get kicked to the inner system. Now the problem is that most of the stuff that's far out is icy and will get evaporated much more quickly than the rocky stuff. So I actually favor that the stuff on the interior, even though it has a harder time of it during the star's evolution, because it's rocky, will survive better than the icy stuff far out. So I actually worked on an idea where I took the thought experiment of our solar system, and I just measured, and I put a whole bunch of asteroids, our own asteroids in our solar system with the known orbital elements, and I ran them through an n-body simulation where I made the sun evolve through its end of life, and then I just watched what happened between the asteroids and Jupiter. And what I found was that asteroids that were in the 2-to-1 mean motion resonance with Jupiter, an interior resonance with Jupiter, would get kicked in and tidally disrupt a few at a time at a rate of, a few per year or a few per tens of hundreds of years, depending on how long it had been running. And you can compare these models with the observed accretion rate of a population of white dwarfs to see if the model makes sense. So what do I have here? Okay, so the blue points are my simulations. The red and black points are white dwarfs that have metal lines only. The red ones are metal lines and dusty disks. And you have sort of my simulations explaining sort of the weakest accretion rates over time. So this is temperature of the white dwarf, which is sort of a proxy of evolutionary timescale. White dwarfs go from being hotter to colder with time as they cool down. And this is the mass accretion rate. So if you just took sort of an average of my models and you kicked it up by a factor of 10 or 100 or more, I can't remember now, let's say a few hundred, you would roughly match the highest accretion rates that we actually observe. So maybe we have solar systems that have a lot more rocks than we do. Maybe that's one explanation. Now, I worked with a summer intern for a while, and instead of having a small number of asteroids, we put as many asteroids as are actually observed in our solar system and tried again. And when you put a lot more, you get a lot higher accretion rates. So now it's more like we need only like 10 or 20 times what our own solar system seems to have in terms of a reservoir of tidally disrupting planets. But this is sort of like a proof of concept. We can get asteroids that start out very far with a resonance to a big planet, Jupiter or Saturn, and they get kicked in. And what's happening is it's because Jupiter is getting more muscly. Okay? So Jupiter, over its evolution, there used to be a ton of asteroids right here at the 2-to-1 resonance. This is the 2-to-1 resonance. But what would happen is once they got caught here, and eventually, so this is semi-major axis of orbit for the asteroid versus eccentricity. So they would random walk in this region and then eventually get so high in eccentricity, they escape. They either interact with Earth, they get kicked out, whatever it is. They go into the sun. But when the sun loses its mass, suddenly Jupiter is much stronger. And so everything that was on the edge here is now trapped in the resonance and starts moving around until it gets to the white dwarf and causes a dust disk and causes dust. And we can even probe, with these simulations, the distribution of how much material gets and how close it gets. So if you remember, we were seeing dust rings that were sort of in this region here, right? And so what you would expect is if something came into 60 white dwarf radii, it would shred up here, and then all the dust would sort of drain in that way. So the outer extent is a rough measure of where the asteroid maybe came in. And what this is saying is that you expect more things right at the edge of the tidal disruption radius than really deep into close to the white dwarf. So that's interesting. It also means there's a whole bunch more stuff just outside that's hanging around, waiting for I don't know what. But there's a whole bunch of stuff that doesn't get tidally disrupted that's just hanging around. It might collide. If the white dwarf is particularly hot, the stuff out here will evaporate stuff off. Keep that in mind. You've got number 8 or 9. I don't even know. Okay. Anyway, So now we can do the same calculation where we compare to a larger sample of observed white dwarfs with different accretion rates and the simulations. And now, so the solar system looks a little wimpy still, but this is sort of like your most conservative estimate of how much mass you would get accreting onto a white dwarf. But we still measure sort of the bottom fraction, but we're only like a factor of 10 or so, and at least at early times for our solar system, we can even match the highest accretion rates that are observed. But our solar system will eventually weaken pretty quickly. You know, you run out of stuff, and it slowly falls to very low accretion rates over time. And so then these are the times after the star dies, you know, as mapped to the temperature of the white dwarf. So we still see quite a bit of accretion in nature that we don't expect to see from our own solar system planetary architecture. So we need to investigate different planetary architectures to sort of get a hint at what maybe is causing the higher accretion rates that we actually observe. Okay, I'm going to skip that. Not very interesting. But I will tell you about a mystery. So I mentioned that Kepler had discovered many, many planets. Well, it also found something extremely weird around a white dwarf. A piddling, faint little white dwarf that everyone had ignored for many years. And someone, during K2, so remember Kepler had a main mission, its reaction wheels failed, and now it has this new mission called K2, which is doing great stuff because now it's looking at wider swaths of the sky. And they looked at this one white dwarf, and someone noticed that the darn thing kept dipping at a period of about 4.5 hours. And then when you add everything up, you see these strange dips that are pretty small. Now remember, white dwarfs are about the size of the Earth. So any dips are from small things, smaller than the Earth. So these dips look strange. There's no way to put it. It doesn't look like a planetary transit because the dips are not regular like a transit. They're all over the place. They're kind of strange. We think we're actually seeing disintegrating asteroids in real time. Because what's happening is we're seeing these dips that are either very sharp or sort of asymmetric. And so we're seeing bits that are sort of like a comet tail, right? So we get these asymmetric profiles from the tail crossing in front of the white dwarf. And it's happening over and over again. So there's like a collection of bits going around and around. We don't really understand this yet. Literally tomorrow I am jumping on a train. I'm going to New Haven. I'm going to be observing on the Keck telescope on this object all night long. I'm just going to sit on it and see if it does something weird because it keeps changing. These dips don't stay regular. They change in depth. They shift around in time. This is like a paper that came out a couple weeks ago. I didn't even put the reference. Sorry, apologize for that. But they noticed, okay, this is a weird plot. They call it a waterfall plot. What's happening is these are all the observations they took of the star. And anytime you see a blue feature, these were a series of dips. And they were able to match up those dips from night to night, right? They just sat on this thing over and over and over again. They noticed that some of the dips were sort of drifting in time. So what they interpret is happening is you have a main asteroid or something, Ceres, let's say, and there are chunks of it popping off and then swirling closer and closer to the white dwarf. That's what they're interpreting these dips and the drifts and the dip times as. And when you do that, you can actually constrain the mass of the planet, or planetesimal, from how fast things are drifting. I was not aware of this, but they claim this is true. So if they got that right, they think that this planetesimal that is breaking off these chunks is about 1/10 of the mass of Ceres. So Ceres is one of the largest asteroids in our asteroid belt. So something about 1/10 the size of Ceres is not crazy for our solar system. It would not be crazy for another solar system as well. So this is starting to fill in a picture. This is sort of like the best example of a dusty white dwarf because not only do we have these dips, so we're seeing the disintegration in real time, there's an infrared excess. So we can go with James Webb Space Telescope when it launches, and we can look at the spectrum of the dust and understand something about what the dust is made of. We can see the bits sloughing off. We can maybe take spectra of the bits sloughing off and get the dust composition that way. And then when we take spectra of the white dwarf itself, it has tons of metal lines. So we can get the composition of the dust in the white dwarf. We get every step of this process with these observations. It's a really unique system, and it's very exciting. So, yay. Now, if we can see asteroids, we can see a big Earth-like planet, no trouble. An Earth-like planet will make significant changes to the brightness of a white dwarf if it goes in front of it. So this was thought of a couple of years ago. Some people have some really crazy ideas about how you could maybe even see atmospheres around these planets, even like industrial waste from civilizations, stuff like that. But I am interested in saying, can we find habitable planets around white dwarfs? Because white dwarfs evolve very slowly. They don't flare. They don't do much of anything. They're about as common as G stars in our local galaxy. So if they host planets, which these dusty white dwarfs seem to suggest they host planets in some way, maybe these are also places to look for habitable planets. You have to get very close to a white dwarf to be habitable. So you have to somehow, okay, if you look at this, so that's good from an observational standpoint because you don't have to look at any particular object for very long to see if it has a planet because it has a nice big signal and a short period. Great. Problem is it has a short period, which means that you somehow have to get a planet that would have been destroyed during the star's death, somehow getting very close. So we see that asteroids do it. It's a little bit harder for planets. So there's no reason to expect that there are a lot of planets close to white dwarfs, but it's so easy to look, we might as well. And we only have to look at a few thousand white dwarfs to find to put any kind of interesting constraints on the frequency of habitable planets around white dwarfs. So, and one of the nice things is if you have a planet with an atmosphere, that signal is very, very small for main sequence stars because the transit signal itself is very small. With a white dwarf, you don't have that problem. So if there's a planet around a white dwarf, and if it has an atmosphere, it will be easily accessible in our lifetimes compared to the Earth-like planets around main sequence stars or like Earth-like or Sun-like stars that would be very hard to do. And especially if we look in the ultraviolet, there are these large, comparatively to the visible, signatures of, say, oxygen or ozone. So I work on an ultraviolet instrument. I used to work on the COS-STIS team, and now it's the COS team. But anyway, COS has this really nice ability that any spectrum it takes in the ultraviolet can also be turned into a light curve because the detector records the time and location of every photon that hits the detector. And so any spectrum that's ever been taken by the COS instrument over the last 5 or 6 years is also a UV light curve for free. So I have a friend here at the Institute that developed software to turn every COS spectrum, whether people wanted it to or not, into a light curve. And so I asked him, can you give me all the white dwarfs, please? And there were about 100. And then I asked my high school intern, Phoebe Sandhouse. She's now a freshman at UMBC. So keep an eye out for her. I think she has a bright future because she taught herself how to program a computer, how to do research, and she found out that within our white dwarfs, some of them had been observed so many times that you actually could have seen for a range of periods things as small as Pluto or maybe things even as small as Ceres. That's how sensitive COS is when you have a lot of light and you're talking about a white dwarf where the signals are large. So Phoebe did this. We have a paper that is accepted by the Astrophysical Journal. It will be out soon. But basically she discovered that if you wanted to, if you found a transiting planet around a white dwarf, you could follow it up with Hubble and get exquisite precision, especially if it was an Earth-like planet, down to the levels that you would probably need to look for an atmosphere. So let's hope COS doesn't die before we find an interesting transiting planet. So James Webb will be very useful too. You can look at planets around white dwarfs in the infrared just as easily as you can in the visible or in the ultraviolet. There's a mission called TESS, the Transiting Exoplanet Survey Satellite. It's going to look all across the sky for transiting objects. So it will look at a few thousand white dwarfs for free. And so we will be able to maybe, hopefully, answer the question of whether there are habitable planets around white dwarfs. And if there are, if you find a lot of them, then they may be the most common type of habitable planet in the universe. So we have, M dwarfs as a good candidate for habitable planets because we've actually found some interesting planets in close orbits. We have Earth-like planets around Sun-like stars. Those are also very interesting because we have one habitable planet that we know of for sure, us. And then a whole bunch of other candidates that might be interesting. And then after them, white dwarfs are actually the next most common type of star. So if we can prove that these stars have planets, just like all the other stars we seem to find that have planets, well then we'll be in business. We'll have 3 different types of stars to understand planet formation about. And even if we don't find any planets around white dwarfs, that's okay because we certainly see the fingerprints of rocky planets around white dwarfs, and we can get a really good idea of how rocky planets form in the universe. So, dusty white dwarfs. They have tiny little disks. They are caused by asteroids that shred up. The dust turns into a disk. It eventually accretes onto the white dwarf, and you get a fingerprint of the dust's composition, right? Elements and relative abundances. And then we are actually seeing this disintegration in real time around dead stars. And we think there might be a lot of planets around these white dwarfs that are really interesting to follow up on. I should also mention that James Webb will actually be sensitive to find Jupiter-like planets at large separations from their white dwarfs, presumably the perturbers that cause all these dusty conundrums. So with that, I'm just going to advertise a citizen science project that I'm part of called Disk Detective. So if you like dust, or if I have suddenly convinced you that dust is the most amazing thing in the universe, you can look for more dusty stars with Disk Detective. It's through the Zooniverse website, and that's a fun thing to check out. You'll help us find dusty stars yourself. And with that, I will be happy to take questions. Thank you. Yes?
You can do any simulation analysis to see whether in our solar system, the Goldilocks zone would move out as our sun kind of increased?
Right. So I haven't done that, but there are people who have looked into that. And yes, what happens is the region where you can sustain liquid water expands as the star becomes a giant. But the problem with that, or maybe it's a problem, maybe it's not, is that the star is evolving pretty quickly. So it gets big pretty quickly, and then eventually it goes out. So we think that that's probably too quick for life to spontaneously generate and evolve into people that drink coffee. But there are periods of evolution where the star would be a bit brighter. So when it first starts fusing helium, it's sort of steady for a while until it runs out of the helium. That's probably the next longest time, and that would push things a little bit further out. But yeah, when we're a giant star, Titan will be pretty nice. Yeah, beachfront property.
How quickly do some of these objects disintegrate? I mean, is it something?
Oh, the planetesimals?
Yeah.
Well, yeah, that's a great question. I don't think we have a good answer for that yet. I personally did a few dynamical simulations, and what I found is that at least in the first pass, what happens is the asteroid gets shredded, but then it all just goes back out again because there's really nothing slowing the material down. You would think maybe that all the energy would dissipate in the disruption, but that's not what we found. And another very talented researcher, Dimitri Veras, who's done a lot of work on this kind of thing, found that through mutual collisions of the chunks that get torn apart, you eventually get something that settles down maybe after a few hundred orbital timescales. But the question, it's not clear to me whether that's orbital timescale is very close to the white dwarf or that full eccentric orbit where, basically it started a few AU out and came in. So you were talking a few hundred years, maybe, you would finally get things settling down into a nice disk. So the question is, do we see a whole bunch of nice regular disks that have already settled down, or are we seeing different phases of that settling? And that's still a very much open question, because each system looks a little bit different. You know, we don't really fully understand the structure of these things because all we have are a few photometric points. And that doesn't really constrain the structural property or the spatial distribution of dust very well at this point. So there's still a lot of questions about how this all works, but we think we sort of have the general picture. And this is one of the few times that I can think of in science where we had a really crazy explanation for an observation that required a lot of moving, complicated parts. And it actually, as time goes on, it's become the best and best explanation, because as we get more and more observations, this crazy idea of some random planetesimal far out getting kicked all the way in and disintegrating is what we keep seeing. So our next step really is to tie what we're seeing directly to some planets that are further out. And we're not quite there yet, because we just don't have the sensitivity to those far out planets. They're old, cold, far away and small, and so we can't directly image them very well. Maybe we can do something with Gaia where they have like astrometric sort of precision where they could maybe find some planets. Radial velocity surveys wouldn't work because white dwarfs just don't have enough lines to get precise velocities. So there's very few ways to actually find planets far away. And that's what's limiting us right now and really pinning down how all the steps work.
Other questions?
You mentioned something about the Kuiper belt objects being culprits.
Being culprit, yes. They also could be. We actually find some white dwarfs that have accreted water-rich material or carbonaceous water-rich material. They seem to be rare compared to the ones that just seem to be pure rocky. But there's still a question of whether, if you have a lot of Kuiper belt objects that are sort of like hunks of rock with a layer of ice, the ice would go away, but the hunk of rock would stay. But if you have a bunch of dirty snowballs that are just dust and ice mixed together more finely, that would just turn into little dust clouds that would dissipate before they would accrete onto the white dwarf. So depending on what fraction of dirty snowballs versus icy rocks we have in the Kuiper belt, which I don't think is a solved question yet, it may be those are a contributor, but it's not clear to me how much. You also can do, it's much easier to do it with one planet with the sort of rocky interior asteroid belts than it is with the Kuiper belt, because with the Kuiper belt you need more than one planet. Which, we're also finding is fairly common, that there are multiple planet systems more often than not. So maybe that's not a real limiter. So we might be able to find through the composition what the relative rates are, but we're not at the point yet where we can say this was a comet, this was an asteroid. We can broadly say this was rocky.
Okay, so John, I have a question.
Sure.
Mario Livio would say that the sun isn't going to go red giant. That it requires a 2 solar mass star to go red giant. And a lot of what you did uses our solar system as a proxy for what you're seeing in these. If indeed Mario is correct and only 2 solar mass stars and above can go red giant to go planetary nebula and such, would that change significantly or actually help your ideas, because it would push you to a higher accretion rate, possibly?
Yeah, it would certainly help because you would destroy less material and presumably you'd have more planets surviving as well. So maybe you'd have Earth and some other things surviving. But at least for the more canonical stellar evolution models that people have done, even though it may not have quite the same evolution as a 2 solar mass star, the sun, at least from what I've seen, still is predicted to get pretty large, if not like super huge.
I had the argument with Mario, and
Right.
he's adamant with his conclusion.
Mario's never wishy-washy. So.
No. As they speak of astronomers, we are never in doubt, although often in error. Any other questions from the audience? All right, I have one more question. Guys, you talk about habitable planets around white dwarfs, but your plot showed maximum of like 40-hour orbits.
Right.
Okay, so we're talking about orbiting an entire star in what is essentially one Earth day.
Yep.
Does the term habitable really apply there?
Right, so depending on who you talk to, some people say you can't get any sort of habitability there because you'd be tidally locked. So what that means is you'd have one side of your planet facing the star at all times, which eventually, some people say due to tidal interactions, would actually kill the planet. It would just sort of mush it up and make it too hot, or it would crash into the white dwarf. So that potential is certainly there. These are orbits that are just outside the tidal disruption radius, so the planet should be physically okay. But the details of how the tidal evolution of a planet around a white dwarf, that's still probably an open question because I don't know how well we understand tides in that sort of situation. So I prefer to be optimistic. It's so easy to find these things that I think we will either find them or we won't. And then if we really, I mean, it's really, you know, you don't have to do this to like the third significant figure. You basically have to say, are white dwarfs orbited by more or less than about, you know, if 50% of white dwarfs have some kind of habitable star or less, which we can constrain with by looking at a few thousand white dwarfs, we basically rule white dwarfs in or out as interesting targets to look for habitable worlds. So I think we can do this experiment once or twice with existing technology or soon to be launched technology, and then sort of be done with that question. On the way, we'll find really interesting things like these disintegrating planetesimals.
Okay. All right, last chance for questions. I don't see anything. Blah, blah. There was a question online. I wonder what influence JWST might have regarding this field. And you actually did mention, you answered that during the talk.
Well, I can answer it again.
Say
It's going to be huge.
Give that advertisement.
Yeah. Also, since that's where our bread and butter will become for the next 10 years, I'm legally obligated to promote James Webb. But in this case, it's pretty easy to do. I don't have to really be forced to do it. But James Webb, because it'll have spectroscopic capability in the mid-infrared, not only will it be able to find maybe the planets that are perturbing the planetesimals, it will also directly characterize the dust that we see. So some of the brightest disks that we've already found with Spitzer and WISE and Hubble, those will be characterized in very fine detail with James Webb's spectroscopic capabilities, either through NIRCam or MIRI. Both of them have the ability to basically do the same kind of fingerprinting of the dust, but now we're looking at the stuff in orbit. So if we can find a lot of white dwarfs that are accreting, and so we have very exquisite compositions in the atmospheres, we can compare them to the fingerprints of the dust already in orbit, and that tells us something about how well we understand the atmospheres of the white dwarfs, which gives us that predictive power for the chemistry of this dust. So that'll be a really good test of how well we understand those physics. And hopefully we'll get a consistent answer, but we probably won't because that's the way science works. We never have things all figured out.
All right, we're approaching 9:30, so I got to cut things off. Next month we have Rachel Austin speaking. Please come and join us, and let's give one more hand for John.
Thank you very much.
So, I mean, this is really cool. I was going to, if we had more time, I was just going to emphasize just how cool it is you can actually throw the rocket down far away that its light has been redshifted from visible light toward the infrared light. So it's better to see this galaxy cluster using infrared light. Okay? This galaxy cluster is measured to be about 10 billion light years away. Okay? It's 10 billion light years away, which means it's seen as it was 10 billion years ago. So the question is, all right, this is about 4 billion years after the Big Bang. The question is, how large of a galaxy cluster can you grow in 4 billion years? Let's find out. So we're going to take that Hubble image and we're going to color it yellow. All right, we're going to do a composite image. All right, and we're going to take all that Hubble image and we're just going to call it visible, even though between you and me, it's really more infrared than visible light in this Hubble image, okay? We're going to use the Spitzer Space Telescope to observe it deeper into the infrared. Okay, Spitzer is an infrared telescope. Doesn't have the resolution of Hubble, but it can see further into infrared, which is better for seeing these higher redshift clusters in order to see the infrared emission from them. And this is going to tell us a bit about these higher redshift galaxies. But to really get great information about it, to try and measure clusters of galaxies, we want to go to the X-rays using the Chandra X-ray Observatory. Now, these clusters of galaxies form by the mergers of smaller clusters, and the gas in between the galaxies, as the clusters merge together, gets heated up until it's millions of degrees and glows in X-rays. And because the energy put into that gas is indicative of the amount of energy, of the kinetic energy of the galaxies colliding in, the amount of X-ray emission is proportional to the amount of mass in the cluster. Okay? She'll get a little bit of a bigger font because she uses a shorter title there. All right. And if you are going to come to those talks, as those of you here found out tonight, and those of you on the web might find out if you come, that the San Martin Drive, south of the Space Telescope Science Institute, will be closed until approximately September 2016. If you come to visit us, come to the auditorium, you must approach from the north, from the University Parkway, okay? All the details are available at this web address from Johns Hopkins, but all you really need to know is what's here. Just come at us from the north, all right? You can find out information about our upcoming lectures on our webpage. If you just put Hubble Public Talks into your favorite search engine, you should come up with this webpage. This webpage was redesigned last month. Excuse me. It has links to the online live events so that those of you who want to watch at home, if you are sick next month, you can watch live online, both on YouTube and on the STSCI webcasting site. We have the archives of stuff that's on YouTube or in the STSCI webcast archive. We go all the way back to 2005, so that's like 10 years of astronomical goodness for you to enjoy. We also added to our website webpage an easy way to subscribe to our announcements emailing list. The 1 or 2 emails that I send every month reminding people of the upcoming lectures, as well as telling you when the webcasts have been posted and where you can find those webcasts, which is useful. Also, on the right-hand side, you can see the links to the upcoming lectures. About that email list, if you don't want to use the easy way, you want to do it the hard way, you can by going to maillist.st. And mother's like, oh, you've gotten so big. When did this happen, right? Well, we astronomers do the same things, but this time for galaxy clusters, okay? So here is a galaxy cluster in the nearby universe. It's called the Coma Cluster, okay? And the Coma Cluster is one of the largest galaxy clusters. It's got thousands of galaxies in it, right? And we have estimated the mass of the Coma Cluster, and it's 2 quadrillion solar masses. Now, I know some of you think I just made that up, all right? But I didn't, okay? It goes million, billion, trillion, quadrillion. Okay? And the mass estimate here is actually 2 quadrillion. All right? It's 2 times 10 to the 15th solar masses, which is a really big number, but it's a number that I'm going to need later on in this for comparison. Okay? So 2 times 10 to the 15th is your comparison number. Remember that. We'll get back to it. So as the galaxy cluster we're going to talk about is not Coma. It's this one called IDCS 1426. Okay? And this galaxy cluster looks kind of similar to Coma, lots and lots of galaxies. But there's a clue when we look at the wavelengths in which Hubble observed this galaxy cluster. Because you can see the blue in this image is 606 and 814 nanometers. Blue in visible light is actually around 400 to 450 nanometers. Right? The blue in this image is actually red. The green and the red in this image is actually the near infrared. So all of the filters used to observe this cluster go from the red into the infrared. Why would we do that? Well, because this is a high redshift cluster. All right? The galaxy is so sci.edu, clicking on public lecture announce and providing your email address there. Or if you really want to be lazy, just write it down on a piece of paper and hand it to me at the end of the talk, okay? And I'll make sure you get added to the email list. If you would like to contact us in other ways, we have the email publiclecture@stsci.edu. comments, questions, and yet another way to sign up for announcements. We got way too many ways on that. All right. Social media. If you would like to follow us on social media, Hubble has Facebook, 2 Twitter accounts. We're on Google+, we're on Pinterest, and maybe a few more. I myself have a blog, Hubble's Universe Unfiltered, on the Hubble site. I'll have a new posting on Friday. Okay, I don't post very often, but I got there's a new one coming up on Friday. I'm on Facebook, Google+, and on Twitter, but I'm only occasionally on those devices because social media can just eat up way too much of your time. Unfortunately, the sky is not clear tonight, so we will yet again not have observatory after the talk. This is like 3 or 4 months in a row that we haven't had this. I apologize, I don't control the weather. All right, people may call me the master of the universe, but I cannot control the weather for you. So, but if you go to marylandmd.spacegrant.org, the Maryland Space Grant Observatory, you will find their webpage and their information about their open nights on Friday nights, I believe. Every Friday night, that's clear, again, subject to the weather, they will let you look through their wonderful telescope there. Okay? So go to their website page and find out about that. Let's take it to our news summary, News from the Universe for March 2016. Our first story tonight. When did this galaxy cluster grow so big? I mean, every time my kids see their grand... there. There, we got that. Okay, let's take the house lights down and we shall begin.
LEDs.
Laser pointer works, okay. Good evening, ladies and gentlemen, and welcome to the Space Telescope Science Institute's public lecture series. It is my joy and pleasure to be your host. I am Dr. Frank Summers of the Office of Public Outreach. For the gentleman who just came in late, you didn't get a pretty picture yet. The pretty pictures are down there on the corner, and tonight's pretty picture is the Butterfly Nebula, also known as NGC 6302. This is a dying star, which is of significance for our speaker's talk tonight because he's talking about, I'll just go straight to it, Planetary Tales from the Stellar Crypt, Exoplanets Surviving the Death of their Host Star. This is John Debes, who has spoken to us before with all sorts of interesting titles, but I gotta say, John, your title is so long that you get a small font. Okay, all right, you get a shorter title, you get a bigger font on the slide here. Next month, we have Rachel Austin talking about why we need to understand stars to find the next Earth. And in May, we have Tom Brown talking about On the Trail of the Missing Galaxies, the oldest stars in the neighborhood. And you'll see that both of them will also get similarly small fonts on their title slide. But Nicole Lewis in June will be talking about probing worlds beyond our solar system.